Hi, this is Steve Brightfield, Chief Marketing Officer at BrainChip, coming to you from the Consumer Electronics Show in Las Vegas. We are talking to key partners, industry analysts, and leading developers of electronics products in the market to get a feel for what is in the future for AI, particularly AI at the edge. Today, we have two special guests, Dr. Jonathan Tapson, Vice President of Engineering at BrainChip, and Dr. Alan Wilson-Langman from Sigma0, a key consultant for radar technologies across many industries and many companies. Welcome and thank you for joining us. I'd really like to know how radar is going to impact edge AI and how you see it migrating from big military systems to everyday products.
Great. Thanks, Steve. Thanks for the introduction. This is John Tapson, for those of you who need to pick up the voice. I think everybody's aware that drones and air taxis and a number of unconventional aircraft are starting to explode in usage. And for all of these things, there's a need, both civilian and military, to understand what is in the environment around you and not just know that there's an object there, but understand what kind of object it is. And obviously this is particularly important in the military situation where there may be only a few milliseconds within which to actually formulate a plan of reaction. And certainly in the civilian path as well. I think everybody in the FAA lies awake at night worrying about drone collisions with commercial aircraft. So these are exploding problems, if I can use that overloaded phrase. And so micro radar and edge radar is going to be a really interesting topic in the years to come. And so that's one reason why we were happy to be able to sit down with Alan, because he has an extraordinarily broad experience of radar in these kind of environments. So it's just really nice to hear what he's got to say.
Thanks, Jonathan. Hey, Alan, welcome.
Thank you very much
for joining us here. Yes.
Pleasure.
Tell us a little bit about your background, Alan. It'd be really interesting. You're both doctors. Did you go to school together, or did you know each other from university?
Yes, we did. So we're both at the University of Cape Town, which has a very strong, actually, radar group there. A lot of radar work was done in South Africa. In fact, one of the oldest radar stations is down on one of the coasts. Beautiful place to visit, and from the Second World War. So it's
Fascinating, yes.
Great history, you know. And prior to that, at the University of Cape Town, just to kind of mention, there was sonar. One of the researchers out of that went and worked for a company developing RadarSat, which is one of the first synthetic aperture radars that's still in production today, providing a lot of really important value to the Canadians and others. So it's got a really strong heritage of radar kind of research, along with other signal processing. And that's, you know, both of us were at that department. So
Great. Well, I have to convince you that my first job out of college is working for the U.S. Navy doing radar and sonar signal processing. So I'm pretty out of date of the technology, and it would be fascinating for me to hear how this has really transformed when it was analog going to digital signal processing, and now going from digital signal processing to AI processing.
Yeah. So, I mean, Alan is he's been polite. He was very much a radar expert, whereas I was more of an instrumentation and machine learning expert at that time. But I imagine one of the big steps was changing to multi-source, multi-receiver kind of situations.
Yeah. MIMO radars. So there's been a strong development of radar technology in the defense industries. We know that. There are enormous teams in Boeing and other these companies developing this technology. And these are all for scanning the skies. They've got lots of antennas, transmitters, receivers, and they're sophisticated processing. And then a couple of years back, in probably 2017, when the FCC opened up automotive, suddenly everyone else got what they call MIMO radars, which are, they have multiple transmitters and multiple receivers. They have exceptionally broad bandwidths, which means a lot of information processing. And these are very complex radar devices that are out there. And but it's very new kind of technology, kind of takes, you know, people by kind of a bit of surprise. But so that technology, yes, it's what ultimately, when you're looking at designing any radar system, what you're trying to do is determine where something is relative to your radar system on the ground. And so the first thing you do is you have this bandwidth that gives you range, right? So I know in some, if I look at a sphere going out, break it up into smaller spheres or sub kind of shells, and that's where you can detect things. But then you have two objects which are it's based in angles, you can't determine what they are. So then you need another dimension. So you need more antennas in elevation. And that's where you can then determine that angle. And then radar is extended to be able to look in the next dimension, which is the elevation. So now you can see where it is relative to a particular system. And so that's why you need these multiple antennas. And then for different applications, you choose what those antennas, how their patterns look, to be able to optimize not just resolution or angular resolution, it's information, it's detections that you really cared about. And it's the state information that you get out. And why this important is radar, unlike cameras, it's a coherent signal. So it adds and subtracts. So little reflectors about an aircraft all come combined. Sometimes you can't see it, sometimes you can. And so when you are tracking and you capture your detections, and then they feed us this algorithm state estimation, so you can have a better idea that there is something there moving at a certain speed.
If I can interrupt you, that's a profound thing that I hadn't really thought through. That if it's video, you get a frame, and intrinsically the frame has got all the information that you need. Whereas with radar, it's the time development of the frame is going to actually carry a significant amount of information.
In fact, you're measuring time delays principally in radar, correct?
But also just that this moment's reflection isn't going to give you the same information as the next moment, simply because of the phase changes.
I see.
And and for us at BrainChip, that's really interesting because we are specializing very much in understanding time development of signals. So it's just another reminder of why we are seeing such good results from our systems on radar classification.
So radar, though, has been in development for a long time, like you said, and most of that has been done with digital signal processing for decades, in fact. What's driving the introduction of AI to radar processing systems?
AI is a different processing technique, in terms of, so you have your information that's typically radar is about detections. The information that you get out of it is about the change of the dynamics of a system as it moves with time, or the local dynamics happening on it. And for radar, those paths out moves is used to differentiate and kind of define things. Then you want sort of obstacle kind of recognition. You try and understand what's happening. But what that reflections are actually mean and how it relates specifically to an object. So let me give an example. If I have a drone, one drone, its propellers orientating, right? They have another drone, they rotate differently. So what they do is they change the microdoppler signatures from their platform. So as the platform moves, that's your general Doppler. So once you estimate that, you look at how the movements happen. And that unique information is very complex because it's a complex interaction. Now, to try and have sort of standard DSP or understand the linear algorithms in doing that is really hard. You have to figure out the maths. It's very complex. And so machine learning and AI provide the tools to handle that complexity, as long as you have the sufficient data to do that. And so now people have a need they want to classify as well. So a lot of companies will produce a point cloud, which are the detections, and they'll label the point cloud with a classification. That's a human and stuff. But often they do that just purely on snapshots. And I think moving to the time series is fundamental for radar and fundamental for the AI, because the change of time of anything is critical in that information, because over time, the signature changes too, but it's correlated. And so it's very, very important, what's being done. That's why I'm kind of really excited about what BrainChip's doing.
Yeah, so we're excited about that because, as Alan mentioned, this idea of state and of evolution of state. And BrainChip's new architectures are really, really good at state modeling and state classification. And so just the alignment of this with our silicon architectures is a very exciting.
So what class of neural network models would you deploy in radar that take advantage of that?
I think state space models are going to be the really interesting ones here. State estimators, technically. But what do you think, Alan?
Well, this is absolutely, this is kind of what's happening. So AI for radar is different. So firstly, the signal's different, right? Fundamentally, it's coherence, so it's got a much different statistical distribution to others. So it's not, in the early radar work, people use CNNs, which is not really a great way of doing it. It's nothing more than just, curve fitting on that. And what people have realized, to really constrain the neural networks so they don't make the wrong decisions with radar and the sparse data that's available, you have to constrain the neural network architecture. So you have to introduce that physics. So it's almost model-based deep learning, approaches. So instead of extracting features from a model-based sort of system, understanding comes scattering, it's really being able to constrain it correctly, so you still have all of that dimensionality to be able to reliably have it fit correctly and predict correctly.
That really fits well with our TENS architecture
does.
strategy
It does.
then, which is physical modeling of these
does.
space networks, correct?
It does. And then you mentioned sparsity and just, if you don't mind me asking, do you want to just unpack that idea a little bit?
So often with radar, if you look out, you see an object in space. It's just one small object, and there's a lot of freedom around it. So you don't have a lot of other objects to kind of resolve. And radar engineers have used it for a very long time to optimize antenna design. Because if you want an antenna with a very high resolution, angular resolution, you need a bigger aperture, right? But to have a bigger aperture, and if you want it to be unambiguous, you have to have more elements.
Right.
And that's not practical. It costs. So what happens if I leave a few out? And so you exploit that sparsity in terms of the antennas, and then also compressed sampling and others use it. But it's for specific applications for radar. And so when you're just looking ahead and it's sparse, but if you're looking at something which is clutter rich, a lot of other signals you don't want, then you've got to be a bit more careful in terms of the assumptions you make. Because sparsity is assumption about your problem. And if it's wrong, your sensor's not going to provide the right observations.
So would you dynamically change the antenna configurations based on that sparsity?
That's a really, really good, question. So MIMO radars are really designed in the way because they link into what's called cognitive radars, right? So what cognitive radars are doing is as environments change, what tweaks can I make in order to optimize the quality of the signal, the observability? Okay. And so if you have enough, so you have transmitters and receivers, for example, you can change the type of waveforms you send out. You can change, what transmits when. You might have different kind of antennas, etc. So that is exploited. So you're not always capturing huge amount of data, but it's slowly being changed. But it's in the beginnings of what's out there.
This is really the innovation you're talking about is happening now, right?
It's happening now.
Okay, I see.
I want to ask a question in a slightly different direction. You mentioned automotive earlier on, and I think most technical people these days are familiar with the idea that in ADAS, which is autonomous driving systems, there's a lot of argument about what sensor package will provide in due course true self-driving capability, whether it can be done purely with video, which has been the Tesla approach for many years, whether it requires LiDAR, which has a lot of commonalities with radar. One could almost think of it as just very high frequency radar, and then radar itself. And are you seeing ADAS providers using radar, starting to think about radar?
Well, I think radar itself has been used by ADAS for a very long time as just general your braking systems, etc. And it's provided it works on your systems. It doesn't work in certain situations, like be driving down the middle of Iowa, and after your roads have been covered in salt and whatever else, they'll tell you, and you want to be told. But most of the time, it provides very robust estimates for cruise control and
Right.
cross traffic, very specific applications where it's been designed, and now it's extending kind of further. So that has been a key application, but it's really challenging, right? So in order to get it out there, you have to drive 1 million kilometers without any false alarms, because you don't want your car stopping.
Is that the standard?
That's the standard. So you really have to, there's a lot of people, a lot of detail that has to be put in, right? So whenever you're designing, whether it's, the AI is not something new that's going to make life easier from design. Problems are hard. They still need to have the same right approach so that you constrain it correctly to get the results. It just allows you to have more variables and handle more complexity.
So it's not how well it works, it's how it almost never fails, right?
Absolutely, because these are safety applications.
Right.
Or autonomy safety applications. So we can't just say it kind of works. It has to work according to, in the automotive, they're very clearly defined, and there's new standards coming out, which even make it more difficult. At night, seeing pedestrians closer to vehicles. And so it's kind of growing.
It's well beyond 6 Sigma. It's like 10 Sigma type of performance, right? Yes.
It's challenging. So, and that's why, one still needs to approach it in the same way defense approach it, but you need to, AI has other applications in accelerating the tool development, right? You can't spend the same amount of time defining use cases. You want to be able to extract that. You want to be able to have existing data to extend. One of the techniques people are using for automotive is we want to use is those last few data points are difficult, but if you can capture the geometries and then use some simulation, you might be able to extend it in a way. But simulation's another story.
Right. So that's one of the interesting things for us is, if you look at ADAS video, there are massive data sets from the likes of Waymo. And if you look at machine learning generally, we have these enormous data sets nowadays. But in radar specifically, we don't see those data sets. So for us as machine learning people at the edge, that's going to be a really interesting thing is how we deal with the data is intrinsically sparse, but the actual data sets are sparse as well in the sense that they're small and few and far between.
Yeah, so and you can't just capture radar data and just try and label that. I mean, that's
Right.
So you have to have radar along with other modalities which are used to train the radar data.
So for example, you'd have vision and radar data and overlay those and use
Absolutely.
that to train the radar models?
Absolutely, that's kind of what helps to do, because I know that's kind of an object. So when I'm in the lights and everything's good and the camera's really working well, that's the solution. But when it's not, then we need the radar, and then the state estimation figures an optimal way to kind of combine it. Still the complexity.
So it's really multimodal models that we're talking about here in the future, right?
Absolutely. So there's two aspects. So there's one is the training of the radar as you go through. The other one is the you're going to be multimodal. And in my sort of unsolicited opinion, it's likely going to be cameras and radars. Why? Because they're most cost effective. They have the biggest differences, in terms of and the value overlapping. Yeah, LiDAR's great. I love it. It's beautiful, but it produces a lot of data, which you have to process. And also, it doesn't work as well in all the environments, and the cost hasn't quite come down to the levels. The challenge, we haven't exploited radar to the level yet, because radar can operate close to performance in terms of the resolution you want with the LiDAR, if it's needed. But if they can provide that extra modality to be able to combine with cameras to get it, you instantly have velocity, right? Straight out.
Yeah.
You don't need a special FMCW kind of LiDAR to do that. That's there. Localization, which is absolutely key. That's another critical aspect, because with a radar system, you don't need to understand your scene to be able to determine localization. You just need that scattering from the ground and understand how it captures data. So there are use cases that make it really, really applicable, but it's that fused one that's going to provide the solution, for these automotive going forward.
So one of the challenges is, like you said, cost, not just of the sensors, it's also the computing power that you need to do these type of things. A lot of these, prototype systems are rolling supercomputers, right? And the question is, how does it become a mainstream product? And do you really need a supercomputer to process all this data in radar processing?
So I see one of the big challenges, just maybe before that, is that these problems are unbounded in terms of understanding many of them. And so you've got to have a system that learns. So the first thing, whatever solution you have, it's got to be the ability to change it up, up top. That's kind of key. Secondly, you want to provide the right amount of compute at the right time, at the right place. And if all you need is a certain processing, and it fits better in architecture, that's what you need to use. Low power is critical, because you can't have a lot of power on a machine that's going to die, that's going to fail as well. There's a lot of those challenges. More data means more failures. You're successful with the minimum solution set to effectively solve that problem. In aerospace, I was saying to people, and I was talking about just a general alternative, they'll tell, well, what's the minimum you can do from a processor, because we've got to certify all the code. Right. So there's those aspects as well. So I'm very, on the edge, you want just the right element, the right amount of processing with the low power to be able to solve those problems.
So we don't have too much time, so maybe you could summarize to me, how do you see BrainChip's architecture, impacting this future roadmap of radar, and what do you see kind of happening in 2025?
Sure. Well, 2025 is going to be a really exciting year for us, because we can speak about in broad terms. We have some very exciting radar projects going ahead with some prime contractors to the U.S. Aviation industry, and for us, it's about just reducing power and latency and particularly size and weight as well at the edge. So if you're flying a small drone, if you're flying an extremely fast object of some kind, you want that minimum payload, maximum performance, and I think we're so excited about how BrainChip's architecture maps Pardon me. We're so excited about how BrainChip's architecture maps to this problem, and particularly our recurrent and state space platforms are going to be really, really effective. So 2025 is going to be fun. We're going to do some good stuff.
Thank you so much, Jonathan. Do you have anything to add?
It's just exciting to see this technology and to potentially help map some of these radar algorithms onto. I definitely think it's a great, as John mentioned, when you have a drone, it's electric, you want the minimum amount of electronics on it, and yet you want to optimize that compute, just the right information to solve the problem.
Well,
And I think BrainChip has that, and it's exciting to learn about it and to help make it successful.
Well, thank you so much. I think that was very illuminating for myself and hopefully for our listeners as well. And I really thank you for joining us, both Dr. Tapson and Dr. Wilson-Langman. Dr. Wilson-Langman. And we look forward to seeing some results of this work in 2025 becoming public. Thank you so much.
Thanks, Steve.
Thank you, Steve.
Thank you.